All right, I guess it's time to start. Welcome, everyone. Welcome to the last session for CppNow. After this, we're all gonna rejoin and watch the closing keynote by Bryce to see what should come in the C++ standard library. But until then, I'll have to entertain you with a short journey. And it's a story of my quest for a better crash. You're going to learn a few tidbits in this presentation, but you should take it more like a case study or an exploration to see the path my team and I took in exploring some of the concepts that I'm going to present in this talk today, relating to how to handle situations where the application would crash and how to harvest all the required information from that crash to be able to debug and reproduce the context in a remote situation where the application runs and see all the context on the DevBox machine so that you can easily debug and explore what actually happened there. So for an hour and a bit, we're going to talk about this, and I'm going to take you with me on this journey, and we're going to progressively build the infrastructure needed to obtain all of this. And I do encourage you to ask questions. If you have more elaborate topics that you want to discuss, or maybe I'll venture an opinion or strategy there, do ask questions. I'll try to defer maybe more complicated topics or items towards the end of the presentation. We'll have plenty of time, I hope, in our time slot for plenty of Q&A. But if you have questions during the presentation, feel free to use the Q&A tab in Zoom and post your questions there, and I'll try to keep an eye on the Q&A tab and jump in and maybe pause to address some of the questions as we move along. If you have questions and maybe I've moved along or your different questions to the end, try to maybe mark down the slide number. It's in the bottom right corner there. Might be helpful if we have to go back and look at some of the code on that slide. Some of the slides are a bit convoluted in code details. Don't try to obsess over the details in the slides. I try to show everything needed. I've hidden some of the unnecessary minutia for the boilerplate needed. But the relevant bits, I try to highlight the relevant bits, and I'll explain live as we go along. So don't try to read everything on the slide. I'll just point you to the right bits there. Okay. Some of you might know me. I've been working on this application here, Advanced Installer, for over 15 years now, going on 16 actually. And this journey I'm telling you about today is closely related to working on this application and everything relating to instrumenting crashes in production there. And on the side, maybe some of you might know the project I've been working on for the past 4 years now, and that's Clang Power Tools. So this quest I'm going to take you on has really 3 main parts. We're going to try to remember the crash so that we can construct a context and see what we're after, and see the bits that we need to reconstruct that context on the developer machine, not on the actual production machine where the crash happened. We're going to have a fair chunk of the time spent together gradually building this infrastructure and seeing all these bits required. And towards the end, we're going to address how we're going to probably going to deal with this kind of thing in the future once such facilities that I'm presenting today will become part of the C++ standard. So we're going to talk about C++ 23 stuff relating to crashes and stack traces. All right. My presentation, just before everyone settles in, my presentation is mostly Windows. So I'm going to talk about two instruction set architectures here because there are differences in 32-bit and 64-bit Windows applications and how they handle exceptions and stack walking and symbols and such. So it's mostly Windows stuff, but I'm going to touch, like I said in part 3 of this vignette, I'm going to touch on platform and standard concepts that we're going to see in C++ 23 relating to stack traces and some bits that are going to come and some nice to have things that I'm hoping to have, but at the moment it's not so sure. So stay with me till the end to see portable code, not just Windows specific stuff. But most of the presentation, just so you know, it's mostly Windows exception handling and Windows symbols and crashes. So remembering the crash. I think we've all been there, seeing this crash report. Maybe some of you remember Dr. Watson. Yeah, this brings me back. So our old friend Dr. Watson there, constantly investigating and reporting bugs for us. Or his modern friend, Windows Error Reporting, which looks fancier, but mostly the same machinery underneath. But where do all these crashes go? We generally are facing this whole thing from a user perspective. We usually see crashes in other applications, or these Dr. Watson-like or error reporting dialog boxes might pop up, and we're usually facing those as client, as consumers. But what does it actually happen behind the scenes, and how can we opt into this mechanism and leverage it in our application? So these were questions I had over 10 years ago, before any store or Windows Dev Center or any centralized platform to handle crash analytics and stack traces and dumps. So I was wondering, is this even available for third-party Windows apps? Because I mostly saw them in Windows applications and Windows internals applications. How can we register to receive such crash dumps for my application, for example? Does it cost anything? This was way before Azure was a thing, or the Windows Store. How does the crash data look like? Who owns it? Where is it stored? Basically, I just wanted this. I wanted my stack traces and my crash contexts on my machine. So everything else sounded way too complicated. All the answers I found way back then. Today, the situation might be very different, and I'm going to give some hints later on. But back then, it seemed way overcomplicated. And it required custom registration for each app version, running a Microsoft Symbol Server instance deployed on premise, symbol stores and databases. Basically, it was a DevOps nightmare. It was not a developer task. It was more like a setup and maintenance of dedicated infrastructure to handle all of this. So, like any enthusiastic developer, I started to roll my own. So the goals were pretty simple. Needed to be quick to develop, because this was not a task in itself, but something to help with the application. Easy to integrate in our CI/CD, so no special servers, no symbol server, no complicated DevOps maintenance. Zero footprint on client side, so no shipping symbols, because, for example, for our applications, the symbols, PDBs are fairly large, so it can easily reach over a gigabyte in footprint. So deploying symbols on client side was not an option. Zero performance impact on release binaries, on the happy path at least. And easy to use as a standalone tool on a non-developer machine for processing crash reports. I'm going to talk later on about triaging and harvesting these reports on non-developer machines. So these needed to be addressed on with a standalone tool that's easy to use and integrate in a support workflow. So in terms of CI/CD pipelines, it needed to work with Jenkins, GitLab, and build artifacts and storing everything. So when a new build is underway, all the required artifacts are kept for each revision that is built. So we're going to dig into what these artifacts might be. For example, let's say we have a particular commit there. With that highlighted hash, and we have a symbols archive that we need for this particular build and this particular commit, and we also have the standalone tool for processing the crash reports that I mentioned earlier, which is just an installation package for that tool. So basically, the idea is that for each particular build, we need to store the build artifacts required associated with that build, because as you might know, by default, builds in MSVC toolchain are not completely reproducible in terms of the builds are not deterministic. So each time you build, even if you build from the same source, same git commit, you're going to get slightly different debug information and different binaries, because timestamps are involved and some other internals that I'm not going to discuss now. So you can make an effort to have deterministic builds, but it's not on by default. So and it does require some special effort to set up. So this is why you cannot build these artifacts on demand. For example, going back to a particular commit and building those artifacts on demand for that particular commit when you need it the first time. So you have to be proactive and cache these artifacts as you move along. So each release that you make, you need to cache these artifacts because you don't have a deterministic build system. If you do, then you don't have to store them. So you just save up some space and you can build it on demand. So the symbols archives for a release build, for example, contains, among other things, the PDB files for the executables that you want to instrument later. In this example, we have 4 PDBs. As you can see, some of them are fairly large, so it really helps that this build artifact is zipped nicely together, because actually PDB files compress fairly well. And you do need to have full debug information for release builds and archiving symbols. Visual Studio has had for the past few years, I think, an option to generate a faster. It's called debug fast link. It's a incremental. It builds incremental PDBs to make the development cycle, especially for debug builds, faster. So it actually the link operation is way faster because by default it tries to build incremental PDBs. This actually is detrimental for archiving. So there is a tool in the SDK that you can use to consolidate all those incremental PDBs and build the full PDB from all those incremental PDBs. But I think it's a hassle. And in the latest versions of Visual Studio, actually building a full PDB database has gotten much faster. So the need for debug fast link, in my opinion, is not really necessary anymore. So we used to do the fast link option when it was launched a few years back, but nowadays we just do the full link and the full debug PDB synthesization on each release build, because it's just way faster now. So you do need this when you archive your symbols, because otherwise you're going to get all the incremental chunked up symbol files. So basically, what you want is to see a full stack trace, not a dry one like this one without any symbols. This one has some context that you can attach to and drill into, but it's definitely not a friendly site. So you don't want to see a dry stack trace like this. You want to see something more meaningful, something that as you're trying to explore it and bring it in your IDE, and you try to jump in to debug the problem, you want to immediately see a starting point, a hook, somewhere to start with. So you want to be dropped in exactly where the crash occurred, where the problem is, and you want to see the full stack trace, how you got there. You want to see your environment, you want to see the memory and everything. So I'm going to talk a lot about context and what it means and what's the useful information that you can gather from each thread and its crash context. So what you want is when your application crashes, you want to be able to collect these crash reports that are anonymized, and you want to these crash reports, of course, they have no symbol information in them, because on the production machines, you don't deploy symbols. And you want to collect them through a support service, and later on symbolicate them and triage them and bring them to the developer machines where they can be debugged. So this is a mock-up of the Symbolicate tool. And the workflow, you select the build that caused the crash. The crash information has the required build signature, for example, the git commit hash. And you have the DCM symbols, the build artifacts associated with that build. You can retrieve them from your archive. And then you get a full stack trace when you symbolicate the crash. And there you have a handle to start exploring and debugging the application there. And what you want to see is this. You want to see, and I'm going to draw your attention to the first important bits in this crash. For example, right away we have an access violation, and it's a write through a null pointer here, and you see the address of that access violation, and you see the call stack for how you got there, including source information there, file and line number. So you have to dig in right away. So we have our first clues there. Like I told you, for example, here we have the wizard next function, and we can dig in and see immediately what null pointer access was on that particular line number at 97 there in this example. So how it works is interesting, but we have to make a quick aside and talk about structured exception handling, because if we don't address the elephant in the room, it's going to get really complicated. So I know this is not a popular opinion, but lots of Windows applications use async exceptions. So, for example, we use async exceptions on all our modules, and for good reason. I'll explain a bit why. And lots of Windows applications have to use structured exception handling. If you want to learn more about this, it's a very interesting topic. I'm warning you, it gets complicated, but it gives you opportunities to really hook into the operating system internals and catch all sorts of issues that might arise in your application, as well as address some more uncommon faults that might occur in your application that are not typical error codes or typical throws or typical C++ exceptions. So structured exception handling is important to address, and this workflow needs to support this. Otherwise, it wouldn't be useful for a large portion of Windows applications that actually need this, including mixed applications, for example, with C++ and managed code. So this, in case you don't know, this option is in the code generation tab in project settings. So build with SEH exceptions or async exceptions, or in the MS build file, you can find it in exception handling tag. Again, I'm mentioning here building with full debug information, and also don't run with edit and continue. So the edit and continue workflow, again, was meant to increase productivity when debugging and changing source code. So you can basically keep debugging as you change the source code without recompiling the full application. It's nice, so it's a good productivity boost, but it's detrimental for builds that you need to instrument later on, right? For example, for release builds or for release candidates, or stuff that you need to archive for later instrumentation. Never use things like edit and continue. So /ZI there means just a simple program database, not one compatible with edit and continue. And to handle C structured exceptions, so that those are the primitive operating system exceptions on Windows, you want to handle those as C++ typed exceptions, because otherwise it would be too ugly. So there is help in the CRT to do this. There's a special CRT function, set SEH Translator, and you can give it a custom callback that you can register to receive such exceptions, and you get an opportunity to map them to a C++ type exception. And you can also install an unhandled exception filter. For example, it's a very common pattern on Windows applications, especially when dealing with lots of callbacks from the operating system or interaction in GUI applications when receiving messages and processing messages. People sometimes forget to catch exceptions, and they might leak off the current context without being caught until the outer module main that is in the CRT. So not your application main, but the CRT main, which is the actual entry point of the module. So if you want to trap such exceptions that leak without you being able to handle them, and still get an opportunity to inspect them and react wherever they might occur, without actually having a master try-catch block, there is an opportunity again in the CRT to set an unhandled exception filter. And again, you specify a callback, and the CRT will call you when such an exception escapes your context, and gives you an opportunity to inspect it and react in some way. That way might very well be to terminate the process, but at least you have an opportunity to log stuff that happened, and, for example, archive this information and collect it for instrumentation and debugging on the developer side. So if an exception occurs in a process that is not being debugged, the exception is caught, the CRT intercepts it, and you get an opportunity to intervene. Some exceptions are even recoverable, so it's not always recommended to take that route. So sometimes the safest thing is not let the process limp along and just terminate it immediately, especially if you have memory corruption, because it might get uglier if you try to recover. But at least you have an opportunity to log and archive this information so that you can inspect it and see what happened. This is how it might look like an unhandled exception. You get a pointer to an exception pointers structure that's defined in the SDK. And for example, here we inspect some of the bits in this structure. I'm going to explain later what these are. And we have a helper function, a stack walker trace from context, that can build a nice message starting from this context record in this structure that the CRT gives us. And you can choose how to present this error, or if you want to silently ignore it or log it or anything. And you can just let the application crash or whatever you want here. You have the trans function that translates structured exceptions. So see structured exceptions from the operating system. For example, like access violation. This might be the most common one. But there are other usual suspects here in the case statement. I just listed a few here that you might be interested in. So again, this CRT callback that we can implement, we receive the exception code that tells us what kind of fault occurred. For example, it might be a page fault or an overflow or something like that. And the context that we can retrieve from this exception pointer structure. And from this, I'm going to show you how you can reconstruct all the information needed to actually build something meaningful out of these dry structures. For example, in case of access violation, this might be the most useful one to be interested about. So if we do receive an access violation notification, we can immediately see what kind of operation type we had from this record there. So the first field in the exception information array would be the operation type, and this tells us if it was a read or a write or a data execution protection fault that is trying to execute data. And then you can actually extract the virtual address of this access violation fault. And using these two, you can immediately see if you have, for example, if you have a 0 address, then you have a null pointer involved. And if you have an operation type is read, so it's a read null pointer or a write null pointer, or you can get the picture here from all the combinations that you can get. So you can immediately try to decode what exactly happened, and it gives you a better picture of how to react and how to explore the code once you also get the location information. And I'm going to show that too. So again, we have this helper stack walker that we're going to build, trace from context, and we have the exception message that we're going to build, and we always need a starting point. We need a context record. So again, the context record can be retrieved from the CRT, from this parameter that we receive, exception pointers. And in terms of origin or source location, again, we can retrieve this information from the context record. It's fairly simple. And we can choose how to handle this. For example, we may choose to throw a C++ exception that specifically tells all the information, or it wraps up all this information that we decoded from these ugly structures from the Windows SDK or CRT, and we decoded all this useful information, and we can choose to package all this nicely in a friendly message that is has all the information as text, and maybe throw it as a C++ exception to handle it somewhere else, or we can log it, or we can send it, we can archive it, or whatever. So basically, this step allows us to decode all the ugliness from the SEH machinery in Windows, and decode all that information and package it in a format that it's human readable or human understandable. So what about an exception in flight? Of course, you can get the stack trace for the raised exception on the current thread. Yes, this is thread dependent. So if you have multiple threads and exceptions might occur on each thread, each has its own context, and you have to handle each thread independently here. So basically, you can use the same machinery, but you have to take each thread into consideration because it has its own context. And for example, here we've built a simple utility, get stack trace for current exception, that uses the same trace from context function. We've seen this 3 times already. And for the parameter where it requires an exception context, we have another helper function that gives us the exception context for the current in-flight exception. And this is what it's called the PCONTEXT in Windows SDK. The PCONTEXT structure, it's a ugly, humongous structure. I don't think it's even public API. By the way, lots of what I'm going to show you today, it's undocumented, and some of them are private APIs, very old APIs, but they still work. And everything I'm going to show you, it does the job, but some of the bits I'm going to show you are not properly documented. So I did some digging around and reverse engineer and learned from other open source projects. For example, some interesting things I've learned from the Chromium project. I found some bits in their source code and how they handle this kind of stuff. And it's very useful, but it's not properly documented. So the context structure contains processor-specific register data, as you might expect, and the system uses these structures to perform various internal operations, and they're passed around in such callbacks that, for example, when we register for structured exception handler translation function. For example, this one, PCONTEXT is that second parameter that we pass to trace from context that we've seen previously. In this case, we receive it from the CRT directly, and it's right there in the exception pointer structure. And the exception record. By the way, they're very similar sounding structures, so don't get confused. So this one is the exception pointer structure that the CRT gives us in the translation function. And it contains an exception record and a context. So the next structure we're going to see is the exception record. And the exception record contains the exception code. For example, if it's an access violation or Stack Overflow or divide by 0 or something like that. Some flags that we need to interpret based on the code. So flags have different meanings depending on what kind of structured exception we're dealing with. We have a linked structure here. So we have a pointer to another record. This is a linked structure. We have the address and the exception information that is an array containing, again, different bits of the information depending on what kind of exception we're dealing with. For example, when we dealt with the access violation, it had 2 fields. This array had 2 fields, and the first one was the address, I think, and the second one was if it's what kind of operation, if it was a read or a write, or the other way around. I can't remember. It was on the slide. So again, this exception record is architecture dependent. So we have a different structure for 32-bit and 64-bit. The implementation is slightly different. The exception implementation machinery on 64-bit is more efficient. For 32-bit, the classic implementation is a linked list traversal to link all these exception records. On 64-bit, there are some lookup tables, and the lookup is more efficient on the happy path. So the structures are fairly the same. So getting back to the PCONTEXT, how do we get this? For example, if we're not in the situation where we were informed in the callback by the CRT about a particular context, for example, in a SEH Translator. For example, if we want to get a context in a particular point, and if we want to get a stack trace from a particular point, like on demand, log this stack trace. I'm in a particular point in a function, and I want to see how did I get there. I want to log this entry in this function, because this function can be reached in multiple ways on multiple branches and from multiple colors. Pardon me. So how do we get such a context? Well, the answer turns out to be very complicated, but once you wrap this up in a nice function, it all works. It's different based on what kind of CRT are you using. So for newer CRTs, this is the procedure to get them. Ignore all the details, just know that it works. And by the way, this is the complete code. So there are some special private functions from the CRT that you can call, and some structures that are not documented, but they get the job done. For older CRT versions, if that's still the case, some of you might need to build with an older CRT. There's a slightly different CRT function to get this context, and it on both the older and the newer CRT version, it's different if you're building a multi-threaded DLL or a multi-threaded application. For example, if you're statically linking to the CRT or dynamically linking to the CRT. So if your application is dynamically linking to the CRT and you deploy CRT, or you depend on the CRT on the system, then it's slightly different. Yeah, if you statically link to the CRT, which I do recommend, I know it's not a popular and recommended Windows approach. Microsoft likes you to dynamically link, but I'm not a fan for various reasons. Feel free to ask me why. But if you statically link to the CRT, then you have a different path here in this function. So, but it's all neatly wrapped in this helper. Again, so this is the old CRT. Okay. I talked about these APIs. You're not going to find these APIs easily accessible by a simple include. You do have some dependencies there, like exception handling.h and signal.h to get some of these symbols, but others you will have to declare them explicitly, and the linker will know where to find them. Okay, again, some undocumented APIs here. Mind the magic. Don't get hooked up on the details. CRT Power comes from mainly this structure. And again, I mentioned this is a per thread information. So each thread has its own context and its own exception handling machinery. So this structure has everything you need to get a hold on to the current context and the current in-flight exception, and any translator that might be installed on that thread, and so on. So lots of very useful information, like frame information and unwind information and image information for this module and everything. So it's a very useful structure that you might need for other purposes, not necessarily for exceptions. So getting back to, if I want to trace, I want to see a full stack trace from the context of the color. I'm in a particular function. For example, I want to assert or I want to log that I've reached this point in this function, and I want to see all the possibilities, all the branches that the application took to reach this point in this function. For example, for logging or for exploring something. So when there's no exception in flight, we're not talking about any exception. We might still want to leverage this machinery to get a full stack trace to see like a path that the application took and we reached a particular sensitive point. For example, it might be a sensitive function that you need to take care of or you need to explore, and you want to see every way possible in which it was called in a particular workload. So no exception in flight, but you want to see this context. So how do you get the PCONTEXT there? So trace from color, another helper function that you can easily build. And there's a system API in kernel DLL. It's called RTL capture context. And it gives us exactly this context structure that we need and the one that we've mentioned and referenced in each exception handling utility that we showed earlier. So you can build this structure, basically call this API from kernel 32DLL, and it fills the context structure for you. And then you can use the same utility, trace from context, that we've built earlier, and pass in this context, and it just traverses mines all the information, traverses all the frames, and builds the stack trace for us. So now that we know how to get this context or a pointer to such structure, be it from an SEH Translator from the CRT, or maybe we've built it ourselves, like I've shown on the previous slide. Any way you cut it, you have a PCONTEXT, you have a context information. So you have a place in a thread. That's your context. And I kept showing this function, trace from context, trace from context. In all scenarios, it was the same function, stack walker trace from context. Well, this is where all the bits are happening, where all the information is mined and transformed in a consumable way. So we have the input, this context function, and max frame count is just a limiter you can ignore for now. Everything here comes from the Debug Help Library from Windows. So such functions as stack walk, everything, basically all APIs from Debug Help Library are single-threaded. So calls from more than one thread to this function needs to be properly protected. So you need a synchronization mechanism here. Whatever you want to roll, maybe your own or something standard. But either way, you have to be careful when you're dealing with multiple threads. If you access this function, these functions from multiple threads, you need to protect access to all Debug Help APIs, just to be aware. Otherwise, bad things will happen. So you can copy the given machine context structure, because the stack walk API will modify it each time it's called. So you want to keep a copy of this context, and it's a cheap structure to copy. It's not very large. I don't remember exactly the size. And of course, you can get the current process handle and the current thread handle, because it's important. The thread is important. And we have another utility, a symbol util class that helps in this process to extract all the symbol information for the particular context in this thread. We'll see how it does it. So we're going to have to deal with stack frames. So right now we're at the point where we extracted all the prologue that is useful from this context, and now we have to traverse the stack and see each stack frame involved, starting from the current context and going back color by color to see until we reach the module base address, basically the main entry point in the module. So we have another utility, INIT stack frame from context, that fills in a stack frame structure, and we have a for loop that calls the debug help API called stack walk, and at each step, this structure, like I told you, the context structure is modified when it's the stack is traversed, and we pass in the image type we have received there from the helper function. The thread is very important. Thread IDs, the thread handle is very important, and at each step, this stack walk API fills in the stack frame structure, the one highlighted in red there, and it gives the context to the API to handle the decoding, and we get function addresses, and we get the module's base address. We're going to see why the module base address is very important, because we're going to talk about ASLR and the complications that this introduces in our process. And at each step, again, we use the helper object symbol util to compose a stack frame from a particular address there. Mind you, the stack frame dot address PC. Address PC is the program counter, so it's the address of the current execution of in the stack frame, and the offset is the particular address there. So basically, the compose stack frame function, that's our helper function, we're going to see it, it takes in a virtual address as a parameter. And from that virtual address, it decodes the function name and the source file and the line number and everything from the symbol table. And it's fairly easy to do so. Again, the debug help and image help APIs do all the heavy lifting there for us. We don't have to reverse engineering any PDBs or debug symbols there. There are properly documented APIs to deal with this. So that the machinery to actually walk the stack is fairly simple. We keep calling this API until it reaches the module base address, basically, on a particular thread. And again, we have the base module load address there, the base address. It's needed because address-based layout randomization messes with our address computations. So just in case not everybody is familiar with ASLR. So ASLR is a mechanism introduced many years ago in Windows. Don't remember exactly. I think maybe after the Windows XP timeframe. I don't remember exactly. So it basically, up until ASLR was a thing, each module was loaded at a particular address in a host process. So you can predict each module. When each module was loaded, for example, a process might load different modules, and each module was loaded at a particular altitude or a particular load address, and everything in that module, every virtual address in that module was relative to that base address that the module was loaded at. And this was predictable and easily inspectable. So hackers leveraged this load address to actually hook into host processes and basically derail and exploit the host process. So ASLR is the default on Windows for many years now, and basically it randomizes this module load base address. So each module is loaded at a random address in the host process. So every relative offset of virtual address in that module is relative to that randomized base address. So in this way, you cannot predict where that module would be loaded. So you cannot do address computations predictably. So all this mechanism is good for security, but it interferes with what we're trying to do here. So everything I've told you about here actually precedes ASLR. So when ASLR became a thing, I actually had to patch all this code to work with ASLR. So what we have to do is, because all the context information contains absolute virtual addresses for particular functions, or for particular, for example, for a particular fault, like a crash or an access violation or anything like that. So, for example, for a function, it has a particular offset, and it's absolute. So you need to see how to translate this address relative to this randomized base address of the module that you're dealing with. So a way to do this is to capture the module base address. So as the application runs, so when the crash occurs, or when the instrumentation occurs, not when we are debugging. So when the application is running and the crash occurs, you need to also capture the module base address, because as you're being inside, you're the module being loaded in the host process. You can reach and see your own base address, and you need to store it in the crash information. So we also need to capture this module base address in the crash information. So later on, when we have all the addresses, we can do the address translation and subtract this module base address from all the absolute PC counters there that we have in the crash dump. So we can see the relative addresses and decode it properly with the simple file that we have. So ASLR is a minor complication. You just need to store this base address, and you need to subtract some pointers. That's it. Just subtract some addresses. It's nothing complicated, but you need to take care of it. All right. And the stack frame function, I mentioned earlier, the helper function, init stack frame from context. Let me remind you, it was this one highlighted in yellow here. So init stack frame from context, we have an output parameter here, the stack frame, and the current context, which is the input parameter for this function. So we always start with a PCONTEXT, with a context. And we fill in this structure with all the information from the context. For example, the address stack offset is the ESP register. The address stack mode is flat. We have flat addressing. The frame offset is the EBP register that we have in the context. The program counter offset is the EIP register there. So basically, this is where we do all the decoding. And this is, again, instruction set dependent. So for 64-bit, this information is slightly different. And the image type gives us what kind of image we're dealing with, if it's a 64-bit or a 32-bit image. So again, not complicated, but you need to know how to fill this information in the stack frame structure. This is the 64-bit information. Basically the same registers, only the wider versions, RSP, RBP, and RAP. Okay, just some magic sauce to make it work. I mentioned the ASLR and computing the base address. That's, again, very easy to do. It's just one API, get module handle. When you pass it a null pointer as a parameter, it gives you the module load base address. That's it. It's fairly simple. It's a documented API, very easy to use. You just need to store this somewhere in the crash report. And this is a simple example of how to store it. Okay, getting back to the workflow. So you selected the build from the artifacts you have, where you have all the, for example, let's say release candidates or your deployed installations. You select the symbols that you want, the exact executables that you need to inspect or symbolicate. You select the crash report that you receive from the support server, and you just hit the button and you get the full stack trace. Sounds easy enough. And the Symbolicate tool comes in two instruction sets again. You need to use a specific Symbolicate tool for 32-bit, 64-bit, because it has to match the architecture of the debug process. This tool kind of works like a debugger in terms of it attaches to the process. It runs the process on a developer machine when you actually need to symbolicate it to instrument information, and it launches the process in a kind of in a debug mode. And in order to be able to do that, it needs to match the architecture of the debug process. So you have to have two flavors of the Symbolicate tool to make this work. And again, you can check if you have a valid portable executable. If you're not familiar with PE, portable executable, and COFF image formats, these are the executable formats on Windows, and COFF is the binary object file format in Windows. They're pretty well documented. If you want to dig more and learn more about them, there's plenty of documentation and even tools to help you with this. And you have a StackTrace analyzer helper here. And again, you can switch if you have a 64-bit or not process to match the debug process. And also a COFF browser, which is a helper to help with inspecting images, basically, and inspecting image formats. And debug process launch, like I said, it launches the application, launches your application in an instrumented mode, like a sort of a debug mode, not quite, but sort of. And we get the main module for process. This is a helper function that does enum process modules, and we get the main module for process. And this helps us map the thing I talked about with ASLR, so address space randomization. We get the current module base address. So the debugged process is loaded at a particular address in the host process. We get that address, and we have the one stored in the crash report, so we can subtract them and use this offset between the current load address and the stored load address from the actual production machine. And we use this difference to offset into all the function addresses that we have stored in a crash report. And we have, again, we've seen this symbol util helper there, that basically initializes the symbol handler for the current process and looks for the symbol path. Basically, the symbol path is the PDB. It's nothing fancy like a symbol server or anything. So it looks at the PDB in the debug artifacts archive. And we then call the Symbolicate function, and it produces, it consumes the crash report, and it produces a proper stack trace with all the symbols and all the context information that we need. And the init step I talked about earlier, it's all about handling symbol information and how to demangle symbols, how to handle symbol information in the PDB, whether to load source information and line numbers and everything. So it's everything to do with initializing the symbol information for the debugged process. So basically the input is the PDB file that we have in our build artifacts, and the handle of the host process, not of the host process, of the debugged process that we just launched. And we do this sim initialize, which is a public API from Debug Help Library and from the Windows SDK. And from there, we just set the symbol search path. Again, the symbol search path mechanism in Windows is fairly complicated. Loader looks in various locations, and there are various priorities. And calling this API ensures that the debug process looks for the APIs, the symbol information at the location that we tell it to, as opposed to default search locations that the system loader usually looks for. For example, it looks in particular locations, in particular folders in Windows, or it looks at particular symbol servers that it might reach over the internet. So basically, this is how we force it to look in at the symbol in our build artifacts, in the symbol information in our build artifacts. Again, sim from address there is an API from Debug Help Library, DbgHelp.dll. That's in the Windows SDK, and it's in Windows. Again, you can dynamically call it. This basically gives the demangled symbol name for a particular address. And this information is extracted from the PDBs, like you guessed. Set symbol search path, nothing very involved here. It just basically does what I told you earlier. Makes sure that all the information is looked up in the PDBs. Slide was for completeness there in case you need the code. I'm not going to go into all the details. And the symbolicate function that we've seen earlier, it's actually very simple. Once we have all the bits nicely separated, you get the frames. So you get all the stack frames, and you get the frame address for the first frame. And this would be the base address, the one I mentioned that it's important for ASLR. So the first stack frame, it's always the base module base address. And that's one that needs to be taken care of separately. And then you just iterate through all the stack frames that you got with that helper function, get frames from the crash report, and you process each frame. So this is mostly all the code. And we're going to see now the helper functions here, get frames, get frame address, and process stack frame. So process stack frame, this would be the most important, I think. Again, get frame from address. You receive a stack frame and you get the frame address. Okay, and if the stack frame is the module load address, then you don't need to do any translation, or if you don't have any symbol information for that particular stack frame. It might happen that you don't have any symbol information for a particular stack frame. For example, you might have a particular stack frame that has a Windows API, and you don't have the Windows debug symbols loaded on the system, and then you cannot decode symbol information for Windows APIs, for example. But you can see your own symbols. This is where the ASLR magic happens that I mentioned earlier. It's nothing fancy. You have the frame address that you have computed, and then you have to offset it by the difference between the debug process base address and the StackTrace base address. So the difference between what happened on the deployed machine where the crash occurred and where the load address was here when we debug the process on the developer machine. So nothing fancy here, that just an offset that needs to occur. And we obtain the real address and we decode this information for this real address. And we identify, okay, for this real address, what's the symbol for this address, so that we show the nice demangled symbol for this address and the source location for it. And the compose stack frame for real address there in the last line does all this decoding and displays it as a nice string like we've seen. So compose stack frame receives an address, that's about it. And again, we use the symbol APIs from the ImageHlp library, for example, symbol name from address and symbol source from address to get the name and origin. Origin meaning file name and line number. Symbol name from address, fairly easy. We use the sim from address API that we've seen already. We can dynamically query this API from the DbgHelp.dll. And this API basically decodes given proper valid address in the address space of the process after we've done all the translation for accounting for ASLR, and gives us the demangled symbol name because we did the INIT with the proper flags to get the information how we want it. Nothing too complicated here, just boilerplate basically. And symbol source from address, again, the input is an address. virtual address, and we compute the displacement, and this displacement structure contains the file name and line number. That's it. Nothing complicated, and we can choose to format it as we please. So nothing too complicated here. Just the this particular API sim get line from address, again from Debug Help.dll. So all the magic happens here basically. The Debug Help.dll. This is a well-documented API. Debug Help.h. You can link to this library. You can add the dynamic dependency on Debug Help.dll. It's up to you how you choose to handle it. It's worth mentioning here that we need to make a clear distinction between the process as it runs, the application as it runs and encounters faults or crashes, and what you need to take care of in the application and what happens in the Symbolicate tool. So all the stuff I've shown you today, most of it happens in the Symbolicate tool, but some of the machinery needs to run in the application also to collect this stack trace, but without the symbol information. So bits and pieces from these utilities that I showed you, some of them run in the application proper, not just the Symbolicate tool. So all this nice and well, but you might not be a huge fan of all this custom built machinery. So you might wonder, okay, if I don't want to buy into your proposed infrastructure here, what can I do? So there is a good in-the-box alternative, and this is you might be familiar with dump files or mini dump files, but you might not be aware that there's a revamp, let's say, in newer versions of Visual Studio of the so-called Visual Studio snapshot file. And this is, I think this is the real game changer. So it's basically a mini dump file. So the Windows snapshot process captures the program virtual memory and heap and metadata, and packages all this in this mini dump file. And it has some restrictions in terms of operating system targets, but I think it works all the way down to Windows 7, I think, if I'm not mistaken. And Visual Studio can parse and open this snapshot file and points you at the location where the error occurred. So it really changes the way you can report a bug, or the way you can debug a mini dump file. So up until now, debugging mini dump files was really clunky, and I think the workflow using WinDBG is powerful, but it's a little clunky. So I'm a huge fan of the recent improvements in recent versions of Visual Studio. I think most of the revamp and enhancements came along with the support for address sanitizer on Windows. So when they built the machinery for handling address sanitizer and instrumenting applications with address sanitizer, basically, I think parallel to that, all the improvements with handling via snapshot files came, and I think it's a win-win whether you use address sanitizer or not. So making bug reports using mini dump files and especially investigating snapshot files now, it's much easier. You can even hook into live share feature if you're a fan of that. So you have a mini dump file summary there, and you can operate it in Visual Studio directly. It's a much nicer experience from WinDBG, in my opinion. And you're dropped in exactly at the point you want to be there. you have the StackTrace, the memory window, and all the context information that you want there, the registers and the variables, everything. So it's a much nicer experience. What I showed you up until now, it was like something from the side of how the sausage is made, so to speak. But the user experience is not as polished, as refined as something that you might get in Visual Studio, for example, with a snapshot file. So I do really encourage you to try at least this route of using snapshot files. So you can even start a live share session from a particular context that we have here in a snapshot file, and for example, ask a colleague to jump in, and you can share the debug session, so you can debug together. If you didn't know this, is awesome. So multiple people can see the same session and can debug together. It's really nice. Okay, and I do encourage you to at least give it a try. And the last bit is about how it might handle crashes beyond C++20. So there is a proposal. It's quite old. From what I gather, it's from early 2018, and it's based on Boost StackTrace. So this would be P881. Right now, I think it's in draft 7 or 8. Unfortunately, although it's very old, it didn't make it in C++20 in time. Not enough time, too many things to evaluate for 20. C++20 is a huge release anyway. So I'm really hoping this would be 23. I'm hoping for more stuff than it's in this proposal, but I'm going to be happy with what we get. So I put a link there if you want to read the paper. The header would be StackTrace, so include StackTrace. Again, naming is hard. I've been using StackTrace all along for more than an hour now, but people don't seem to agree on proper terminology there. If you run a poll, people want to name it all kinds of ways. I've mentioned StackFrame, and I've used StackFrame every time, but people seem to prefer various terminology, so pick your favorite. I'm not exactly sure. I'm hoping things have settled down in the proposal then, and we're going to have a proper naming. And it looks like this was the first major library addition to C++23. So yeah, key features desired. All functions should be lazy. So you do not want to query the StackTrace entry information without explicit request. Obviously, you don't want to pay for this kind of thing. Exactly what I mentioned in my custom implementation there. You want a dynamic size for the trace. All available invokers must be stored in a trace. Sure. Implementations allow to disable, enable gathering of StackTraces by a linker switch. Yeah, that's quite reasonable. StackTraces shouldn't prevent any optimization. Yeah, of course, you don't want, this instrumentation happening here and all the StackTrace machinery to prevent the compiler to do any optimization or even do whole program analysis and do link time optimization. So you don't want to interfere here. You don't want to pay anything. And the StackTrace should be usable in a contract violation handler, in coroutines, in handler functions, and parallel algorithms. So you want to have minimum barrier of entry, and you want them to be as lightweight as possible so that they can be used in any context possible. So in interruptible, in suspendable functions, and resumable functions in handler and everything. Key features desired. StackTrace entry description. This would be the stack frame. Stack entry is basically stack frame, as I mentioned earlier, and should return a demangled function signature, like I did in the one I rolled in my own implementation. ToString from a StackTrace should query information from the debug symbols, symbol export tables, and any other sources returning demangled signatures. Again, the same thing we've seen earlier, but in a nicer API. Information about inline functions that have no separate StackTrace entries is welcomed. But I'm not sure how implementers would choose to handle this. Inline functions are, difficult because it's even for debugging purposes, showing functions that have been inlined is no easy fit. Sometimes it gets gnarly. Avoid doing heavy operations in StackTrace constructors or StackTrace entry current. So for each stack frame, computing each stack frame should be quick. So nothing too expensive there. This is how it would look like. You have a native handle type, similar to how, for example, standard thread has a native handle type, which is implementation defined. And you have means to reach out and get this native handle, and you would probably access more information if you take a platform-specific route and use platform-specific APIs to maybe drill and get more information than the standardized API gives you, if you need so. And you have the description, source file, source line, very simple, straightforward APIs. In my opinion, very clean to look at. And StackTrace entry models concepts regular and three-way comparable with a strong ordering. And I think that's a sane choice. Basic StackTrace, again, it has to support allocators because it allocates memory, because it constructs that information, and it needs to allocate stuff for the frames and for the symbols and everything. So a possible implementation would be, for example, with a vector to store all the frames, and means to expose iterators to traverse these frames. Somewhat similar to what I've shown in my hand-rolled implementation there. And means to get the current stack trace, for example, and means to skip a particular number of frames or give a maximum depth, maximum frame count, very similar to what I had like in my earlier slides there. And of course, all this information is a per thread basis. So the M-frame structure and everything is for the current thread of execution. And the allocator, as I mentioned, is necessary for because this utility needs to allocate memory for each stack frame. And when it builds the description and source location information. So we're going to see some examples here. For example, description, source file, and source line. Yeah. For example, toString is overloaded to get a stack trace entry or a stack trace as a whole. And you have output operators like put2 that are overloaded for stack trace entries. So you can output formatted stack frames or whole stack traces. For example, you can see, the way to init such a stack trace is using the current static method. So you say basic stack trace current, and you get the current stack trace. And then you can iterate this trace using the built-in exposed iterators there, and examine each stack trace entry. That is a frame. I prefer the frame naming, but yeah, I'm gonna be happy with what we get. And from there, you can use the nice APIs like frame description, source file, source line, and do whatever you want to with them and compose it and format it as you please. So you can even shorten it even more and use toString, which is overloaded for a stack trace entry, or even more, you can use the put2 operator, which is defined for stack trace entry, or even simpler, use toString and pass it the whole stack trace if you don't care about how it's formatted, and you're just happy with the default formatting there. So it gets even simpler because the stream output operator is overloaded for the whole stack trace, so you can just output the whole thing if you don't care to format it the way you want it. So it can't get any simpler than that. So I'm very happy, and I can't wait to see early implementations from the vendors for this. My personal preference, I would love to see more. So I would really love if this standard library facility would provide more information or more customization points. But I'm happy that at least we're going to have a standard way to address this and avoid all the gnarly bits of platform-specific code that we need to roll to handle all this workflow. So I'm very anxious to see how easy it would be to replace all our specific Windows machinery that I've shown in these past slides with the standard implementation once it becomes available and somewhat stable. So I'm really curious if I'm going to be able to replace everything and not lose any functionality that we deem important for our workflow. So I'm really happy to see this in the standard. Okay, with that, I'm going to see if we have questions or maybe chat. If you have any questions, feel free to post them in the Q&A tab in Zoom, or if you want, you can reach out to me on Discord, or maybe there's already a running discussion in the track channel in Discord. I'm going to follow up on that after the stream ends. We can chat on the Discord channel for the track C discussion. If you have any questions or you want some clarifications, or maybe I glossed some of the details, or you might have some particular insight or advice for me, or any other questions, feel free to post them there. I'll try to go back and read the whole conversation there. If you have any questions here now live on stream, feel free to post them until we close the stream. And just as a reminder, the whole week we've been watching awesome sessions from lots of speakers. I'm sure they all appreciate feedback, as I would. So don't forget to fill in the surveys and give speakers feedback, what you liked, what you didn't like. I think constructive feedback is very well appreciated by all speakers at this conference. So don't forget to fill in those surveys that you've received. It really helps. So, for example, I'm very interested to read your comments as well. So again, you might feel comfortable with an anonymized format rather than posting stuff on Discord. It's up to you. So any questions here live on stream, or we're going to move the discussion to Discord. I don't see anything in a Q&A tab. I see a lot of chat, but it's very hard for me to follow the chat stream here. I see void star all the things. Yeah. When you're dealing with these kinds of APIs, it's a funny comment. So when you're dealing with these kinds of APIs, casting to void and reinterpret cast is like bread and butter. It's unavoidable. Any more questions now? If not, I think we're gonna adjourn here and encourage you to reach out on Discord or in speaker surveys there. Okay,